Hi everyone, this is Santosh and I'm a PhD student at Rutgers University. Today I'm going to present our work Fast Deep Learning-based simulation with microarchitecture agnostic traces and instruction embeddings. This work was done in collaboration with Amir from Google DeepMind. So starting with microarchitecture simulations, they are tools that we use to evaluate the performance and behavior of a given microarchitecture design. So for simulation, we have the microarchitecture design and the benchmark is input. And after simulation, we get the performance metrics for those benchmarks on those specific microarchitecture configuration. And then we use these performance metrics like cycles per instruction as a feedback to improve our design. And it has application in hardware design space exploration. So starting with traditional microarchitecture simulation, we have an example of GEM5. So GEM5 is one of the state-of-the-art cycle level simulator. So for simulation, we do cycle level modeling for GEM5. So that means we simulate each cycle of the processor pipeline, and then within that simulation it figures out the dependency between this instruction and then continue doing cycle level modeling for the instruction and then give us the latency of the instruction or other performance metrics. So this kind of simulation is detailed, but it's very slow. It may take weeks or months to simulate real workloads, which is a big problem. And they are slow due to highly irregular and difficult to parallelize workflow, which cannot leverage modern accelerators. So on the other hand, so overcoming the limitations of traditional simulators, we recently have machine learning based simulation. So for machine learning based simulation, instead of designing a software model for microarchitecture, we replace that software model with a trained machine learning model, and we do instruction-wise prediction of latency. So here we do one shot prediction for each of the instruction, and then we get the overall cycles for these instruction. So this kind of workflow is highly regular and parallelizable, and they can leverage modern accelerators like GPUs and TPUs to do fast simulation. Now let's see how existing state-of-the-art work SIMNet works. So for SIMNet, we have two-step process. First step is training. So we collect different benchmarks and we perform detailed simulation to get the timing information from the traces. And then we train a model based on that information. And after we have a trained model, we can simulate an on-scene benchmarks. So here for simulating program Y, we need to do functional simulation at first to generate these microarchitecture specific traces. So the traces includes instruction information and other hardware architecture dependent information like cache behavior and branch behavior. And using that as input, the model predicts the cycles for that instructions. And the simulation error when compared against GEM5 is 2 to 6%. And if we look at the simulation throughput, they are really fast, giving us like 3 or 4 magnitude speed up when we use multiple GPUs. But they have some limitation. The first one is we have to regenerate the trace and do manual feature engineering whenever we change the microarchitecture, because different microarchitectures have different behavior and hardware components. We need to redesign that. And the second one is limited output matrix. With only cycles as an output matrix, there is limited information that we can gain from simulation. And the third one is longer training time. If we include the training and trace generation overhead, then the overall simulation would be 17 times slower than GEM5's. So we also need to further improve that. Now let's move towards our contribution. So first contribution for us is microarchitecture agnostic feature engineering to remove trace generation overhead. So the question is, what kind of input features should I use for the model that could represent the performance? And from the input trace, we collect mostly microarchitecture independent features. So these are opcode registers, mem address, and branch address. So we can reuse the same features for different microarchitectures. And after we have this information, we do some static feature engineering for opcode and register. So we use integer mapping and bitmap vectors to get the features used to be used by model. And for dynamic features, which represent the impact of which represents the processor state due to impact of earlier instruction, we use memory context queue and branch context queue to get this kind of memory and branch history information to the model. So after we have these input models, what would be a good design for prediction model? So for this microarchitecture agnostic trace, we first build the instruction context. So contexts are basically those earlier instructions that can impact the current instruction. And the first step is to build instruction embeddings. We first build categorical instruction embeddings, and then we get per instruction embeddings. And then we use multi-headed self-attention layer to figure out the dependency between the instruction and then correlate that with performance metrics so that we can accurately perform these metrics like fetch cycles, execution cycles, branch misprediction, and data access level for the instructions. Now that we have the model, the next question is how we can simulate on-scene microarchitectures. So for simulating on-scene for a microarchitecture, we need to train a model specifically for that microarchitecture. So whenever we have a new microarchitecture that we want to predict on, we need to retrain a new model for that from scratch because we have the same input, but the performance metrics are different. And the reason is that we have no hardware parameter as input to the model, and the model has to capture all the variation. Now, the question is how to make earlier models reusable and reduce the training time. So our solution is to use shared embeddings layers. We train these shared embeddings layers with prediction layers from different multiple microarchitectures. So we have one embedding layers, and then here we have two prediction layer A and B. And then we train this shared embeddings layer with these prediction layers. Now we can train this model, but we will have some issues on training for uh, for for convergence. So we use linear embedding projection layer to project the embeddings from common shared space to microarchitecture specific space. And then we use gradient normalization so that it can resolve the gradient imbalance issue. And with that, we have a shared embeddings layers. And then the question is what would be the combination of microarchitectures that we can use to train shared embeddings layers? We have more details in our paper. Now for evaluation, we have various benchmarks from spec, and then we have we randomly sample some design space for experiment. And while comparing with the state-of-the-art simulators, SimNet, in terms of accuracy, we have similar accuracy as SimNet. We have slightly higher error because of microarchitecture agnostic input that we use. And in terms of speed, it's 18.6 times faster compared to SimNet and 3.66 times faster than GM5 when we also account for the training overhead. In conclusion, we have a reusable design for deep learning-based simulation, which achieves 2 orders of magnitude speed up over state-of-the-art DL-based simulators. The design is modular, and it also provides embeddings, which can be used for downstream applications like program optimization. I would like to thank NSF and Google DeepMind for their support in this work. Thank you so much.